Right. Hold on. Yes. So maybe Sushil has asked this question, and one or two also have asked this question. So this was, hold on, just a minute. Just make this thin. Okay. So, this is exercise, or this is question number 27. So question 27 from this book, Joseph Pack. Okay. I'll very quickly write down the question. The question was, suppose that Z is the stereographic projection of zeta. Is there a network lag? Somebody?
Yes, sir.
Yes, sir, we are having it. Okay.
I don't know. From yesterday, there is a network issue. Hold on. Just a minute. Since yesterday, there is a network issue. I don't know, like, what is the problem. Achha, hold on. I'll ask somebody to share the internet. Hold on, okay? Give me 5 minutes.
Okay, sir.
Just check now whether it is clear or not clear. Okay, let me write something. Zeta, eta, and xi, and 1 by z. Is it okay now?
Yes, sir, it's okay now.
So suppose that Z is the stereographic projection of this, and 1 by Z is the projection of eta prime, sorry, zeta prime. So the first question was, show that this is this minus eta and 1 minus zeta. Okay, so first part is very easy. So I will not be doing much from the first part. I'll just tell you the idea, and I'll do the second part. What is the second part? Show that the function 1 over z and z in C is represented on, this is the stereographic projection, sphere by a 180-degree rotation about the diameter with endpoints minus half, 0, half, and half, 0, half. Okay, so first try to understand the question. Okay, what does the question says? The first part basically says, if you know the coordinates of z under the stereographic projection, suppose the coordinates of z is this under the stereographic projection, then knowing this you can easily find out the coordinates of 1 by z easily. It is this minus eta and 1 minus zeta. So this is the first part, says that if under the stereographic projection the image of z is this, then you can easily find the image of 1 by z this. So the proof is extremely simple to the first part. I'll just give you the ideas behind the proof of the first part. Okay, so I'll not do the whole of first part. So it's easy. Suppose z is x plus iy, okay, and under the stereographic projection z is mapped to zeta, sorry, this is not zeta, this is so this is eta and this is zeta, okay, xi, this is xi, I guess, so xi, eta and zeta, okay. So what we know under the stereographic projection, you know the relation, how to convert them. So the relation is, this will be x by x square plus y square plus 1, this will be y by x square plus y square plus 1, and this will be x square plus y square by x square plus y square plus 1. I hope I have written everything correctly. So you have to find the image of 1 by z under the stereographic projection. So 1 by z will be nothing but 1 by x plus iy. If you simplify this, so this is x minus iy by x square plus y square, and that is nothing but its real part is x by x square plus y square, and the imaginary part is minus y by x square plus y square. So if 1 by z, the image of 1 by z is this according to the question, then what we know, we can easily find this. What will be this? Can you tell me? You have to find this. What will be this?
X
Real
upon x
part.
square plus y square but divided by x upon x square plus y square का whole square plus minus y square plus x square upon y square का whole square plus 1.
That's good. So you see, if you know this, if z is known to you, then how do you find this, the first coordinate under the stereographic projection? You write down the real part and then modulus of z whole square and plus 1. So if this time this is the complex number has this real part and this imaginary part. Okay, this real part and this imaginary part. So using the formula of stereographic projection, what I have, the real part of this, which is x by x square plus y square and divided by modulus. So modulus square. So this will be this square plus this square. So x square by x square plus y square whole square plus minus y whole square is y square again. So y square by x square plus y square whole square and plus 1. So do you have a problem while writing this? So just using the formula and just start simplifying this. So therefore this is x by x square plus y square. So if you take the LCM in the denominator, this will be x square plus y square whole square, and then this will be x square plus y square plus x square plus y square whole square. Just take the LCM and send the denominator in the numerator. So this one part will get cancelled. So this is x over again, and there is one more thing remaining, x square plus y square, and this is x square plus y square. If you take common, this will be 1 plus x square plus y square. So this is again, this thing will get cancelled. This is nothing but x by x square plus y square plus 1, and this was nothing but this. You see, right, x by x square plus y. So I approve this part, that xi prime is actually xi. Similarly, if you compute for eta prime and zeta prime, you'll get the resulting things. I hope rest is up to you. So I'll go for the second part. So do you have a problem while understanding this? Okay. Now the second part. Now see, second part has nothing to do with complex analysis. It is dealing with 3D geometry. So you should know some basics of geometry. I'll try to explain few parts. So even I took a lot of time to do that second part. Okay, I got only one source from where I can get this, but that was also not that easy. So I'll try to explain you all, but remember second part is something to do with 3D geometry, but I'll try to explain. So what does the second part says? Show that the function 1 by z, z in C, is represented on the sphere by a 180 rotation about the diameter with n points. This and okay. So let me try to draw something roughly. So this is my, let me first draw the sphere. So this is the sphere. So here is the origin, it passes through the origin, right? So this is my x-axis, this is my y-axis, and this is my z-axis. Or not x, y, z axis, actually zeta, eta, and then okay. This is 0, 0, 1, you know, this is 0, 0, 1, the north pole. The center is at, what is the center? Can you tell me? 0, 0, half, right?
0, 0, half.
right? 0.
Yes, sir.
Okay, okay, 0, 0. So let me plot this diameter. I'll try to first explain you geometrically, then I'll show you a short proof. The diameter has n points minus half, 0, half. So minus half, 0, half. So the radius is half. So this is half. So what is the first point? Minus half, 0, half. Minus half is on this side. Here will be someone minus half. So this point will be minus half, 0, half. Okay. And half, 0, half. So half, 0, half will be this one. So this diameter we are talking about, this diameter of the circle we are talking about, sphere we are talking about. So what they are saying is, understand the question first. The question is, if you take any point here, and which, so this is this point, okay, this corresponds to actually Z. This is actually the image of Z under the stereographic projection. If you rotate this point by an angle of 180 degree about this diameter, if you rotate this point about this line by an angle of 180 degree, you will get, after rotating, you will get a point something like somewhere here, and this will be the coordinates of 1 by z. This is what the question says. Show that the function 1 by z is represented on this by a 180 degree rotation above the diameter with endpoints this and this. So the question says, you give me any point on the sphere. If you rotate that point by 180 degree angles about this diameter, you will get the coordinates of 1 by z. So did you understand the question? First, you tell me this.
Yes, sir. Yes, sir.
Now,
Yes, sir.
my first point is this diameter is parallel to the z-axis, basically. This axis, okay? The diameter is parallel to this axis, right? Because you can look at the coordinates and tell me that clearly it is parallel to the z-axis. Maybe not from my diagram, but you can just imagine the situation and you can clearly see that this will be so I can actually bring this diameter here. This will become exactly, this will be coincident with the z-axis. It is just the shifting of z-axis by half. If I take any point here, if I add half to that point, I'll reach on this line. Okay. So this is what you have to see. So we'll use some change of axis and everything. So the first thing what I'll do, so few things to note. So if you want to rotate, this is the rotation matrix. Rotation, I'll first, let me write down first. This is 1 0 0 0 0. This is cos theta minus sin theta. I hope you have seen this matrix before. This is the rotation matrix. So if you apply, so this can be thought as a linear transformation. If you apply, so there is a point. If you apply this matrix on that point, so that point will be rotated by an angle of theta about the x-axis. Try to understand my point. Given any point, if you apply this on that point, so what will be the resultant point? That point will be rotated theta angle about x-axis. So this is what is the meaning of this matrix. This is what this matrix will do. So what I have to prove that, so before that, let me write something else also before doing something. So I hope you'll understand. So with the transformation, of the coordinate system, so you take this as, I I am taking something. Just a minute. Hold on, okay, just a minute. This diameter will be parallel to, just a minute, let me check this thing. I have taken the wrong transformation, I guess. This diameter will be parallel to the z-axis, if I am not mistaken. What is your guess on this? This diameter will be parallel to the eta axis, right? Right, so this transformation is wrong. I have to take here half. See what I am doing? I am shifting this diameter. I am shifting this diameter to the x-axis. So zeta is u plus half. Okay. So if you see the u will be what? Zeta minus half. If I subtract half, this will shift to the zeta axis. Okay. And I'm fixing these two coordinates as it is. So now what I have to show is the mapping. The mapping, what is the mapping I have? This mapping, which map this points to this minus eta and 1 minus zeta becomes, so under this transformation this will become u v w map to, so u remains u, this will become minus v. No, there is a problem, there is some problem. Okay. Okay, let me check. So there will be changes in u, I guess, possibly. There will be changes in u, I guess. U will be I'm missing something. What they have done, they have taken this as w plus half, but this will not be the case because the diameter is parallel to the z-axis, not to the zeta axis. I don't know why they have taken here half. Okay, I'll check. I will not waste much time on this. I'll definitely help you out with this one, but I'll check first. Okay, we'll check once again. Sorry for that. Has anybody tried this part? Anyone? Nobody has tried this question. Okay, no problem. Then I'll just check once again. Okay, I am missing something. I don't know what, but the coordinates are coming wrong. Okay, I'll check once again. I'll go to the next question. Again, somebody had asked this question. Just a minute. Chapter 3, I guess. So this is another question, number 7. This is from chapter 3, okay, same book. The question was, show that a non-constant analytic function cannot map a region here means domain, open connected, into a straight line or into a circular arc. So one way to do this sum is, this question is very easy. Okay, has somebody tried this question? Anyone who has tried this question? Okay, so if you have not tried it, the one way of doing this question, so I'll give you two ways. So one way is, so solution 1, use open mapping theorem. So as you have not done open mapping theorem, I'll try to avoid this, but with the help of open mapping theorem, it is a one line. Open mapping theorem says that the image of an open set under a non-constant analytic function is open. Because neither this is open nor this is open, so the image cannot be this. Okay, so if you use the open mapping theorem, then we are done. But because you have not done open mapping theorem, so let me give you solution 2. So this is much more constructive. So suppose F maps a region D into a straight line or a circular arc. Okay, so suppose we are just starting with a contradiction. Okay, suppose there is an analytic map, suppose there is a non-constant analytic map which is mapping a region D into a straight line or a circular arc. I hope you understand the meaning of this. What is the meaning of this? So this map, the image of the whole region, that is f of D, is either a straight line or f of D is a circular arc. The whole image is a line or a circular arc. Okay, so suppose like this region you are talking about, this region is D, and here is your output. So what is this map doing? This is mapping this whole of D to some straight line like this. So this either a image of f is this, or the image of f is like a circle, some circular arc, or like a circle. Okay, so this is what the question says. So I'm assuming that suppose this map maps a region D into a straight line or a circular arc. So I will show that there will be a problem. It will lead to a contradiction. Then there exists constants A and B such that this function gz, which is a fz plus b, this function maps the region D into the imaginary axis or into a circle centered at the origin respectively. So what is the meaning of this? I'll tell you. See, try to understand my point. So whenever you have a line like this, you can divide by a proper constant or multiply by a constant, which is same thing, and you can shift that such that this becomes like this. So there will always exist some constants a and b such that you can always turn this line like this into the imaginary axis. So with that help of the constants a and b, this function gz will map the whole region D into the imaginary axis, or if the first map f was mapping into a circular arc, this will map to a circle centered at the origin. So maybe I'll talk more about these constants later on. So just assume that for the timing. So I'll definitely get some constants a and b such that this will happen if the above statement is true. So clearly G is analytic in the region D. So this is very much clear because f is analytic and I am just multiplying f by a constant and then adding another constant. So that will keep G analytic in the region D. And note one thing, and for the first case, so I'll call this as case 1. This is suppose case 1 and suppose this is case 2. This is case 2. So and okay. So what happens when I have case 1? So case 1, real part of Gz, or basically real part of Gz is constant. Who can explain me this line which I have written? For the first case, why is the real part of this map Gz is a constant? Can somebody explain me why is the real part of this map Gz is constant when the image is the whole imaginary axis? The answer is very simple. The image is this line, and in this line the real part is always 0. That means it is constant. So this is just an imaginary number. The real part is, instead of saying constant, also I can properly say indeed is 0. Do you agree with me now?
Yes, sir.
Yeah. So now you have done a theorem in class. Sir has done this theorem. If G is equals to U plus IV is analytic, in a region D, and U is nothing but real part of G is constant, and what is the consequence of this? Then
G is constant.
G is constant.
G is constant.
Right. So this theorem we have done. So since real of Z is constant and it is indeed 0, so this gives G is a constant function, and consequently so is f, because f is nothing but Gz minus b by a, and because b, a both are constant, so f must also be constant, so which is a contradiction because f was non-constant. Okay. For the second case, that is G of Z. So what is G of Z? A circle centered at the origin. Is a circle centered at the origin, or maybe some circular arc you can say. let's say just circle, that will no more be a map, I guess, into a circular arc. Okay, so in that case, this implies modulus of gz is constant for all z and d. Can you justify me this? It's easy. Again, it is very easy. So suppose the image is like this, and this is a circle, remember that. So if I take any point here, if this is R, this is also R, this is also R, this is also R. So Gz, the modulus of Gz is always constant, because whatever you take here points, that is a part of a circular arc and centered it at origin. This is why origin is important. Okay, so the modulus will remain same. Again, you have a theorem, you have done this theorem. If G is analytic in a region, and if modulus G is constant there, then G itself will be constant. So what can I say? Therefore, G is constant, and that implies F is constant, and so which is a contradiction. So hence we are done with the proof. So our assumption was wrong, because in both the cases I am getting a contradiction. So a non-constant analytic function cannot map a region into a straight line or into a circular arc. Or you may also use the open mapping theorem, which says that the image of an open set under an analytic function will be always open. Non-constant analytic function will be always open. So maybe we'll do this later. So this was a constructive proof, but you should think more about the existence of this A and B. Try to think more about the existence of A and B. How can you transform a line into this imaginary axis or a circular arc? You can always shift that to the center or origin. Okay. So one more question was there. This was asked by, just a minute, I'll just check. This is rather easy, but chat. Manish had asked me this question. No, not Manish. This was all done. Yes, Manish was that. So this is some question he has got from some book, I don't know. So find the solutions of sine z is equals to 2. Okay. Now firstly you tell me, if z is a real number, is it possible?
No, sir.
No.
Right,
No,
because
sir.
Yes, sir.
when you take z to be a real variable, you know that
Minus
this
1
is
to 1.
bounded by 1. But when you consider z to be a complex variable, then the function sine z is not bounded. So this is what is very interesting. This can actually be any number. You can write here, instead of 2 you can write here 100. You will get a solution. Okay. So the solution is rather easy. So you know that e to the power iz is what? Cos z plus I sin z, and e to the power minus iz will be then cos of z
Cos Z
minus
minus I sin Z.
right. So you can reduce the value of sin z from here. If you subtract this two. So e to the power iz minus e to the power minus iz. If I am subtracting this, I'll get 2i sin z.
2.
Right, 2i sin z. So what is the value I have got for sin z then? So this you should know also. Sin z is nothing but e to the power iz minus e to the power minus iz by 2. So now substitute here by 2i, sorry. So therefore I know, so sin z is equals to 2 will imply, right in the next line, will imply e to the power iz minus e to the power minus iz is equals to 2 by 2, and so this will become 4i. And if you put this as y, so y minus y to the power minus 1, which is 4i. What is y? Where y is e to the power iz. Okay, so this is nothing but y square minus 1 equals to 4iy, or y square minus 4iy minus 1 is equals to 0. So this is a simple quadratic equation. You can solve a solution, solve for a solution. So you can solve it, that is not my part. So y is, you will get two values, 2 plus minus root 3 I. Both the roots are imaginary in this case. So that is, now plug the value of y. That is e to the power iz is 2 plus minus root 3i, and now take logarithms both sides, on both sides. So iz is log of 2 plus minus root 3i. What is the log of this part? Can anybody tell me? How do you calculate the log of some complex number z? What is log z?
Log mod z plus argument of z.
Right. Very good. Plus I times argument of z. Right. So I'm taking the right. So this is nothing but, so okay, before I'll apply the property of log. Okay, so this will become log of the first part and plus the log of second part. I'll shift this to the next line. So iz log of real number will be just this. Okay, I could have also done this. And what is the log of this part? What will be log of I? So modulus of I is 1. So log 1 is 0, right? And I pi by 2, because argument of the complex number I is pi by 2. So this line should come here. Okay, anyways. This line. Right. So if you multiply both sides by I, so this will become, or minus I. I'm multiplying both sides by minus I, right? So this will become pi by 2 minus I log of 2 plus minus root 3. So this is one solution to the above equation, sin z equals to 2. But you know that since sine is periodic, since sin z is same as sine of z plus 2n pi, and n is an integer, so therefore all solutions to sin z is equals to 2 are z is equals to so 2n pi plus pi by 2 and minus I log 2 plus minus root 3, and this n is some integer, right? Okay, so this is all from my side. I'll think more on for the first question. Maybe I had done some mistake. I'll let you know in the next class, and I also hope that sir will upload a new tutorial file before the next class. Okay, So if you have no doubts, you can leave the class. If you have some doubts, you may ask. Stop the recording. If you have some doubts, you may ask.